Hello everyone. So in this Griffin video, I'm going to be showing you how to create process stability while continuously using the Griffin Optimizer. Now the Griffin Optimizer is an awesome tool. It uses a particle swarm optimization in order to test basically a bunch of different potential input values against a model and find which ones are going to best achieve your target criteria. So let's look at what I have set up here. I have this tuning table in which I can adjust my minimums and maximums, also my fixed or not fixed value. Right now in my matrix, I have the initial/fixed value hard-coded at 0.5 for each input. And then I'm also able to input the distance penalty with this adjustment here. I can turn the distance penalty on or off with this value that's being plugged in right here to my distance penalty active flag. Now, in these plots, I have the optimized inputs being displayed here. There are 15 inputs. They range from 0 to 1. This is just my little toy model. And I have the total movement of all the inputs in between optimization runs. So, as you can see from this plot, the inputs are moving around all over the place. And if you set up the optimizer in this naive way, this is exactly what's going to happen to your process. Our target value is 8 right now, and we're achieving 8. But with our model, there's several different ways that we could potentially get to our target value of 8. And if you have, for example, a combustion optimization problem and you're adjusting air dampers, there may be many potentially different values of air dampers that could achieve roughly your target value for something like NOx or CO, depending. That may be what the model thinks. Whether or not that's true in reality is a different question. There are two problems that the inputs moving around this much causes. One is that it's churning your process. It's moving things around when they don't necessarily need to be moved around. Our last solution was perfectly good, so why aren't we just sitting at that? And the other problem is if you're trying to gather data to model the problem space, this is gonna slow down the learning process because we're not spending enough time at any consistent value of our inputs in order to really thoroughly learn that subsection of the operating regime. So let's look at the different tools we have available within the optimizer to stabilize this process. Now, the first thing that should be pretty obvious is that in practice, you're never really going to be hard coding your initial value. Your initial value is going to be most likely your current process value, which I'm feeding into my matrix in the optimized column. So let's go ahead and point that to our optimized values. See, that's our format there, and I'm going to use my text editor trick to speed this up. I'm going to copy all the columns. I'm going to go in here and paste them. Control A, Control Shift L, home button, matrix 1.optimized. Control A, Control C to copy them. Minimize this, and I should be able to paste these right in. There we go. That was easy. Okay, so now we're feeding in our last optimized values. Let's see what happens. And look at that. Our process is perfectly stable now. So that's all well and good. Let's see what happens when we move our target from 8, and we're going to move it just a little bit to 8.1. So ideally, to move our target value such a small amount, our inputs shouldn't have to move very much, but let's see what happens. Okay, so they moved well over a total of 1. So yeah, that seemed like kind of a lot. Let's try 8.11, a difference of just 100th instead of a 10th. Wow, so we still almost moved the same amount, even though our target value changed by an order of magnitude less. So what's happening here is that the optimizer doesn't have any incentive necessarily to pick optimized inputs that are close to what we started with. And that is exactly the purpose of the distance penalty. So let's try this again, but with the distance penalty flag set to 1. And we're going to try to move our value to 8.2, a difference of almost a 10th again. And look at that. That's how much that's the total movement of all the inputs. And as you can see, the change in the graph was barely noticeable. Let's try moving a 100th. Okay, and the change this time was barely even measurable. So that there we are, we're at 5 thousandths of movement. So what this is basically demonstrating is that you're pretty much going to want to use the distance penalty with the Griffin optimizer. It is what's going to allow your process to maintain stability, and also in doing so allow your retraining application to be more effective, because you're going to stay stable at the currently best known operating state until it's proven to be suboptimal, and then it'll move and find something else. With a distance penalty of 0.001 like this, it's basically just enough to incentivize us to stay close to our levels. But you can easily make this value too large and completely screw up your optimization. So let's say we move that to 0.1 and try to go to a target value of 10. Okay, so you see that we stopped at 9.15. And what this basically means is that any further movement of the inputs would result in too much distance penalty that it's not even worth it to try to achieve our objective. If we drop that down to 0.5, I think that's low enough. Okay. So 0.5 is still 50 times higher than what it was when I first did the demo, but it seems to be okay. For my money, I like to use, or at least start with a value of 1,000th for the distance penalty. That seems to be a good ballpark value that will incentivize us to stay close to our initial values without overriding the target criteria. So that's all I have for this video, and I'll see you in the next one.